Hi, and welcome back to Bio 347, Biostatistics and Experimental Design. Today, right now, we're going to go over full factorial ANOVA. Okay. This chapter has much more from chapter 12. There's a whole number of ANOVA designs out there, but two-factor ANOVA, the full factorial, is probably one of the most commonly used statistical methods. Okay. So let's get started. All right. So let's say we're interested in some drug. Okay? And we're going to test another drug. And let's say we're going to just call it drug A and drug B. In drug A, we're interested in the levels. So low dosage and high dosage. Drug B, different take. This drug can be dissolved in water or ethanol. Okay, so a full factorial looks at the possible combinations of these things together. Okay, so we could do an experiment where we just looked at drug A and drug B separately, but by doing combinations, we can do this efficiently. So, for example, we'll have a cohort that gets low dose plus the drug dissolved in water, a high dose plus the drug dissolved in water, another cohort with low dose and a drug B dissolved in ethanol, and another cohort where they get a high dose and the drug dissolved in ethanol. Okay, so let's just add some details. Let's say our replicates is equal to 10. Okay, and what that means is within each combination we have 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are independent from these other combinations. So okay, so if our replicates is 40, what is our total sample size, N? Well, that is just the replicates times the number of combinations. Okay, so we have 4 combinations. So our total sample size is 40. All right, so next, for any one of these, okay, we can pick one, and we'll call that the Yth observation. Okay, it's getting the ith level of A, the jth level of B, and then there's an error term as well, which we'll call K. Okay, so for any observation, what's going to affect this? Well, there's going to be an overall mean, which we'll call me, plus, let's call the effect of drug A alpha, and it depends on what level it's at, so we'll call that alpha sub I, plus drug B, which we'll call beta, and we'll call its levels J, right? So J could be water or ethanol, plus, I'm going to add another one here, and that one's going to be gamma. So gamma IJ, this is the interaction term. So it is one of these four combinations, okay? Plus our error IJK, right? Because not all these are going to have the same mean. All right, we're going to call alpha and beta main effects. Okay, and we're going to call gamma the interaction. Okay, that's the interaction term. And in ANOVA, we're going to partition the total variance. So this whole cloud gets partitioned into these components: the effective A, the effective B, the interaction, and we have our error term, and then the total. Okay, so let's get into how we actually do that. So let's pause. Okay, so the way to express the partition variance is called a source table. So let's create a source table, and let's put our components in it. So some variation will be due to the effective A, some to B, and then we have the interaction term, we have error, okay, and then the total. Okay, so the total simply scales our error, and then we're going to chop that up into these pieces here. Okay, we need to set our degrees of freedom. Okay, so if we have factor A, we're going to say we're going to have A minus 1 levels. For B, B minus 1. For the interaction, okay, we have A minus 1, B minus 1 degrees of freedom. And then our error is going to be A times B, then R minus 1, where R is the number of replicates. And then for the total, it's A, B, R minus 1. And we can just say this is N minus 1, right? So it's our total sample size minus 1, which is the same thing as A times B times R minus 1. Okay, sums of squares are a bit tricky. Okay, let's put our experiment back up here, right? We're going to say we had drug A, drug B, we had water, alcohol, and then this was low dose and high dose. What I'm going to put down here is A sub 1, A sub 2. Here I'll put B sub 1, B sub 2. And let's put sums, because let's just say we're going to take all the observations here and we're going to sum them up. Okay? So we have column 1 total, column 2 total, then row totals here. Okay? All right, our sums of squares. For our sums of squares, A, that's going to equal, okay, we're going to take the sum of our column totals, okay, and we square each of those and add it up, and we're going to divide by R times B, okay, not R times A, but R times B. minus a correction factor. Okay. And I'll describe what that is when we're done. Okay. So for B, it's going to look like the exact same thing. Okay. But we're going to take our row totals, okay, and we're going to take this total here, square it, and then we're going to take this total here, square it, and add those together. So we're going to take the sum of B sub j times R A minus a correction factor. Okay. The interaction terms, okay, so we can look at this as A, B, 1, 1, A, B, 2, 2, A, B, let's see, we're in the second column, second row, first column. We're in the first row, second column. So it's 1, 2. All right. For the sums of squares of our interaction term, we're going to take the sum of each of those cells, okay? So I, J, each of those combinations, and we're going to divide it by the number of replicates R. And note, we need to get rid of the sums of squares we already accounted for. So we're getting rid of these sums of squares, okay, and the correction factor. The error is going to be the total minus all the others. So it's going to be minus the sum of squares A minus the sums of squares B minus sums of squares A, B, so this interaction term, but not the correction factor, okay? Because the correction factor is already within these, okay? And then our total, what we're going to do is we're going to take every observation, square it, okay? So we're going to take every observation, square it up, and subtract by the correction factor. So this is going to be 40 numbers squared added together minus the correction factor. Now let's define our correction factor. Okay. Where CF, our correction factor, is equal to the squared sum of all observations. So let's sum all our observations, y, j, k, and we square that, and let's divide by n, okay? So this should look a little bit more like the sums of squares. This should be squared, okay? So we take these numbers, we square them, add them together, and divide by r. So everything here, I need to square this as well. So everything here is squared, and we're subtracting a squared factor. So this should look a little bit more like the sums of squares that you're familiar with. All right, so that's the sums of squares, and the mean squares are just the sums of squares divided by their degrees of freedom. So we'll do the first one. So that would be sums of squares of A divided by A minus 1. Sums of squares B divided by B minus 1. This would be the sums of squares A, B divided by A minus 1 times B minus 1. The mean square error would be the sums of squares error divided by A, B, R minus 1. All right, let's make some room here and do our hypothesis testing. So we can get rid of just this. All right, here we go. So our F, if you remember, is what we use when we want to do hypothesis testing. So our mean square, remember that this is the ratio, signal to noise ratios, right? That's what F tests do. So the signal of A is the mean square of A divided by the mean square error. So mean square error, okay? The effect of B is going to be mean square B divided by mean square error. And then the interaction term, same thing. Mean square of A, B divided by mean square error, okay? So those are our F tests. The nice thing about all this is R does it for you straight away. No need to calculate anything. What is super important at this point, okay, is that these effects, A and B, it's so important for this F to be correct that these are both fixed, okay? If these are not fixed effects, you will not get the correct Fs and your p-values will be misleading, okay? And we'll go over that when we get to mixed models, okay? So remember what fixed effects are. They are sort of universal effects. So this would be the level of toxins on physiology. Random effects would be things that make these observations non-independent. So time, if you had time, repeated measures, we would not have two fixed effects. Or if B was something like an observer, and we're interested in the effect of the observer, and we had 4 or 5 observers. In that case, the people we picked were random selection, and they would not have a universal effect on our observations. Okay, let's pause, and what we'll do is we'll talk about interactions some more. Okay, let's talk about interactions for a minute. Remember that interactions are what happens when you have combinations of treatments. Okay. Let's look at if we did an experiment and we looked at drug A, and remember we had low and high doses, and drug B, and we looked at it dissolved in H2O and ethanol, okay? And this is some physiological response we're interested in. If we did these experiments by themselves and we got this result, okay? So drug A at low dose, the response is lower than at high dose. So we'll draw this line connecting these two. And water, we had a low response and a higher response in ethanol, right? So these are expectations. Now, we do an experiment where these things are combined, okay? So we can only do one axis at a time. So we'll do low and high. And this is the effect we get. Okay, this is for water. Okay, so we had water was lower and then it was higher. But for ethanol, we had this strange effect. Okay, where ethanol, it was higher as we expected from this experiment here. But then in combination with high doses of drug A, it gets low, right? And then our water at high doses is now high, a high response, okay? So these responses are what we call antagonistic, okay? At least in terms of ethanol, okay? That the response is actually lower than what we expect. So whatever this drug is doing, it's shutting off this response at high doses, the response to ethanol at high doses. Okay? This is not something you could uncover doing these two experiments independently. So that's the primary reason we do these full factorial ANOVAs, is that we can uncover these interactions that we don't see here, okay? And the fact that we get the opposite response at high doses would be super important if these are life-saving drugs, okay? So the main effects are difficult to interpret when you have an interaction. So we could have a response. So our source table may indicate that drug A has a significant positive effect. Drug B, right, that being in ethanol increases the effect. But if our interaction term is significant, this response overwhelms this interpretation. So let me point out that when our main effects, our interaction term, okay, is statistically significant, we need to graph and compare that to the main effects by themselves. Okay? If we get something like this, where we get an unexpected result, we cannot interpret these things by themselves. Sometimes an interaction term is synergistic. And what that would look like is if we had a response from low to high like this for something like water, but for something dissolved in alcohol, okay, that it's even more than what you would expect by itself. This is a synergistic interaction, and that it heightens the response, okay? If we get parallel lines, okay, that means there's no interaction, okay? So if we get a response and we plot it gets like this, we can actually interpret the main effects by themselves. If we get an interaction like this, we can interpret the sign, but not the magnitude of the main effects. So going from high dose increases, so both these slopes are up, and going from water to ethanol increases the response as well. But here the magnitude is unexpected. So it's very different from here. Here there's no interaction, so it doesn't matter the effect of ethanol, right, increasing. Doesn't matter if we're in the low dose or high dose. So here there's no interaction, okay? So our main effects are directly interpretable. So be aware of, one, if your interaction is statistically significant. Two, if it is, realize that you have generally these two responses, an antagonistic reaction, where one thing is actually lower than you expect, and a synergistic interaction where the response is heightened. If you don't have a significant interaction, then your line should be parallel. When we get to our software using this in R, the variable you plot separately like this is called the trace variable. So that'll come up in the future. So our trace variable is the one that will be separated here, not the one on the main axis, right? So you have your y, your x1, and this will be your x2, is called the trace. All right.